In today's lesson, we're going to learn how to make the second type of salt, insoluble salt. At the end of the last lesson, I have left a question with you. Can you provide as many ways as you can to make an insoluble salt, magnesium carbonate? I have received some students' answer from Google Classroom, and also I chose some of the answers from previous year students and make them into a in-class discussion worksheet. So you can download the worksheet from Google Classroom and take a few minutes to go through the worksheet. This is a worksheet that you can download from Google Classroom. So on this worksheet, I have listed out 7 possible ways that you can make a magnesium carbonate. So what I want you to do, first, read through all those methods, and then I want you to evaluate, are these methods good or not? Okay, so how do we evaluate those methods? Remember, when we are preparing any kind of salt, we need to consider 2 factors. First, okay, what are the possible reactants we can use, okay? And we need to make sure that when we put those 2 reactants together, they're going to have a chemical reaction to produce the salt that we want, okay? In this case, magnesium carbonate, okay? And secondly, you need to consider, for some of the reaction, yes, they're going to produce a magnesium carbonate we want, but we need to consider, how do we separate the product from other side product or the unreacted reactants? Is it easy to do? Okay, so these are the 2 factors I want you to consider. So after consider those 2 factors, I want you to use a symbol to state your preference of that possible solution. For example, if you put a tick, that means you think it's a perfect way to make it. Okay, so there's going to be a reaction between the suggested reactants, and also the target salt can be easily separated from the side products and unreacted reactants. Okay, that for those reactions you just put a tick. And for some of the reaction, you know they're gonna have a reaction between the suggested reactants, okay, to produce a magnesium carbonate you want. However, either the reactants used is really hard to obtain or not very stable, or the target salt cannot be easily separated from the side product or the unreacted reactants. So for this one, I want you to put a tick, but also put a line on it. Let's say it's a half tick, half correct, half wrong. That means it's possible, but it's not the best way we can do it. Okay? And for the last type, I want you to put a cross if the suggested reactants will not have any chemical reactions to produce magnesium carbonate. Okay? That means this is impossible. Okay? This way won't work. So now please pause the video, spend around 5 minutes to go through all those reactions and try to evaluate those reactions using the symbols here. And then you can write a few sentences to describe your reason for choosing that symbol. Okay, now I believe you have made your choice. So now let's discuss all those reactions together. So the first one suggested to use magnesium and also react with carbonic acid. And then it will, based on what we have learned in previous unit, if we put a pretty reactive metal into an acid, it will produce a salt and then also release hydrogen gas. Okay, so the first factor, yes, there are going to be a reaction take place to make magnesium carbonate. Okay, and then the second factor we need to consider, okay, can we easily separate the product from the unreacted reactants? Okay, so take a look. Magnesium carbonate we know is an insoluble salt, so in solid state. And the reactants that we used, magnesium, again in solid state. So we will find out that when we drop magnesium into the acid, the magnesium carbonate formed gonna coat it on the surface of the magnesium metal, okay, and prevent the magnesium metal to directly react with carbonic acid, okay, so the reaction gonna stop quite soon. It's similar to the reaction between calcium and sulfuric acid. Okay, so in this way, it's really hard for us to separate the magnesium carbonate with the magnesium. Okay, those unreacted magnesium. Okay, so that's the first reason I would, okay, although it got a reaction, so I can put tick. However, due to the reason that I cannot easily separate the product from the reactant, I will put a cross for that one. Okay, that's the first reason. Okay, hard to separate. And secondly, let's take a look at the carbonic acid chose here. So carbonic acid is made by dissolving carbon dioxide in water, and a lot of the soft drinks that we come across in our daily life, like Coca-Cola, it contains carbonic acid. Okay, so for carbonic acid, it's not very stable. Okay, so imagine this: if you open a fresh Coca-Cola and left it for, let's say, an hour, after an hour, when you drink it, it will have a totally different taste when compared to the fresh one. That's because the carbon dioxide dissolved in the Coca-Cola has escaped. Okay, so again, for carbonic acid, the same question gonna happen. The carbon dioxide that dissolved in the solution gonna escape quite readily. So it's really hard to make sure that you have the carbonic acid that's enough for the reaction to make the magnesium carbonate for you. Okay, so due to that reason, I will put second line for that reaction. Okay, so two reasons. First, magnesium carbonate gonna coat on the surface. Second, carbonic acid not very stable. Okay, so that's for the discussion for the first reaction. Now, let's take a look at the second reaction. The second reaction suggested to use magnesium oxide, which is a base, to react with carbonic acid and acid. So acid-base reaction. And this time, what we are going to get is magnesium carbonate and water. So again, there are going to be a reaction take place, so we can put a tick first. And then let's consider the risk factors. First, okay, so for here, we have magnesium carbonate, which is an insoluble salt. And the reactant we use here, magnesium oxide, okay, remember the solubility table. Magnesium oxide is a insoluble compound. Okay, so again, when you drop magnesium oxide into carbonic acid, the product magnesium carbonate gonna coat on the surface and stop the reaction. So you won't be able to get pure magnesium carbonate out quite easily. Okay, so for that reason, I put a line on the tick. And again, because we're using carbonic acid here, not very stable, carbon dioxide gonna escape readily. Again, I put another line on the tick. Okay, so that's for the second reaction. Let's move on to the third reaction. What do we have this time? For the third reaction, we have magnesium hydroxide. Okay, magnesium hydroxide again is insoluble, and then to react with carbonic acid, again neutralization reaction, so give us a salt and water. So yes, neutralization reaction gonna take place, so a tick. But again, we have the same issue as the previous two reactions. Okay, insoluble salt formed on the surface of the reactant, and also carbon dioxide would escape quite readily. Okay, so again, it's not a very good choice of making magnesium carbonate. Okay, let's move on to the fourth one. Okay, again, it used some of the reaction that we have learned before in the base part. Okay, so this time we use magnesium hydroxide, which is a base, and then we have ammonium carbonate, which is a salt, contains ammonium ion. Okay, so when we put the salt contains ammonium ion with a base, and then we gently warm it. Okay, so although I didn't state the condition, but you need to remember we need to gently warm the two reactants so the reaction can take place. And what are the possible products that generated from this reaction? First, it's going to generate a pungent gas, which is ammonia, and then it will generate the salt, which is magnesium carbonate, and then the side product, water. Okay, also here, ammonia gas is a side product as well. So yes, this reaction can take place, so let's put a tick for that. And then let's evaluate the efficiency of this method. First, can we easily separate the product from the side product and the unreacted reactants? Okay, so side product we have ammonia, which is a gas. It's gonna escape readily, so no need to worry about that. The other side product, which is water, but since magnesium carbonate is insoluble, so it would not mix up with water, so we can easily separate it from filtration, using filtration. Okay, a filter paper and a funnel. Okay, so let's consider the next part. Will us be able to separate magnesium carbonate, the product, from the reactants? So here we have magnesium hydroxide, which is a solid. Okay, that's a reactant. And we also have ammonium carbonate, which is a solid we use here. So again, when we warm it, the product gonna form on the surface of the unreacted reactants. So it's still again quite challenging for us to separate the target salt. So let's put a line on the tick to state that factor. And also remember the condition that we use here. Okay, we need to gently warm the two reactants in order for this reaction to take place. So it requires extra supply of energy to start the reaction. So again, it's not preferred, so I will put another line on the tick to state that. Okay, so let's move on to the next one. For the fifth method, the student suggested that we can use magnesium, okay, the metal, and then put it or mix it with iron 2 carbonate. And then because magnesium is more reactive than iron, and then we should expect a displacement reaction to take place. Then the product formed gonna be magnesium carbonate and iron. Okay, so that's the displacement reaction we have discussed before. Okay, so in principle, okay, this due to the reactivity, okay, we expect this reaction to take place. However, please note that here the other reactant we choose is iron carbonate. Okay, iron carbonate is in iron 2 carbonate, Iron 2 carbonate is insoluble. Hence, it's not a aqueous solution. And remember, when we do displacement reaction, okay, we need mobile ion. Okay, so the less reactive ion must be mobile. So either in aqueous state or in molten state. So if it's in solid state, it's gonna have a strong attraction between iron to iron and carbonate ion, because they are held by a strong ionic bond. Okay, so cannot be displaced by magnesium. So this reaction will not happen. Okay, there is no reaction between these two, because iron to iron is in solid state. Okay, so no reaction, no mobile ion. And then we're left with two other methods. So these two methods, I think we haven't seen this kind of reactions before. Okay, so let's take a look. What's special about these two reactions? The first one, we put in magnesium nitrate, which is a salt, and then together with zinc carbonate, another salt. And then we expect them to exchange their ions. So at the beginning, nitrate is combined with magnesium. So after the exchange, nitrate salt would get the zinc ion. Okay, and then on the other side, the carbonate gonna get the magnesium ion. So it will form magnesium carbonate and zinc nitrate. Okay, so that's a predict product if there is a reaction between these two. Okay, here I made a mistake on when I prepared the slide. I believe I have corrected on your version. So zinc carbonate is in solid state, okay, not in aqueous state, it's insoluble. Okay, so that's for the reaction 6. And then similarly for reaction 7, it got the same pattern. For reaction 7, we put in two salts. The first one is magnesium sulfate. The second one is potassium carbonate. Okay, and after they exchange the cation, then the product gonna form. The product will be potassium sulfate and magnesium carbonate. Okay, so how do we know whether these kind of reaction can take place or not? And how do we call this kind of process? So it's similar to that they exchange the combination of cation and anion. Okay, so we have a special type, a special name for this type of reaction. Now I would like you to open the learning diary and let's discuss this type of reaction first, and I will tell you how to decide whether these two salts will have a reaction when you put them together. Okay, remember in the previous unit we have learned a reaction. For example, we can put copper in silver nitrate solution, and then this copper will displace the silver in the solution and form silver and copper to nitrate solution. Okay, so for this type of reaction, it will have this pattern. A plus BC will give you B plus AC. And for this type of reaction, we call it displacement reaction. Okay, and then take a look at the two reactions that we have come across on our worksheet. For these two, okay, we put in two kinds of salts, and then they exchange the cation and anion, and then form the product. So if we use a letter to represent that, it will have this kind of pattern. It will be AC plus BD, and then it will exchange their cation and anion, then it will become BC plus AD. Okay, so again, because they exchange the ion, so we call it displacement reaction. But unlike the previous one, they only exchanged only exchanged one thing, right? So the BC just give out the B and get NA. So the exchange only happened once. So we call the first type single displacement reaction, or sometimes we don't mention the single, we just call it displacement reaction. And for the second one I mentioned here, you can see AC plus BD and then become BC and AD. So kind of the exchange part happened twice. So for this type of reaction, we can name it as double displacement reaction. Okay, so it give out the salt the first salts AC, it give out the cation and receive another one, and the same thing happened to the second salt BD. Okay, so it give out as cation and receive the other one. Okay, so we say it's double displacement reaction. And for the single displacement reaction, remember we said the ion, okay, the less reactive metal ion must be mobile ion. So we say it must be in aqueous state or molten state, right? So same thing, same requirement here for the double displacement reaction. But here, both of the salts, they need to be in either aqueous state or liquid state. Otherwise, they would not have mobile ions. Okay, so first you need to consider whether they have mobile ions. Okay, if yes, then it fulfills the first requirement. Double displacement reaction would happen when the product contains one of the three products. Okay, so it can either produce water, okay, or it produce a gas, or it produce some insoluble thing, produce precipitate, a solid. Okay, when it fulfill one of the criteria, so it's either A or B or C, okay, then this double displacement reaction would take place. Okay, so remember it's A or B or C. Okay, just need to fulfill one of it. Okay, so if a double displacement reaction fulfill both of the requirements here, then this reaction would take place. Let me give you some examples here. Okay, so we can have a double displacement that generate water, so this reaction would take place. So for A common example would be neutralization reaction between acid and alkalines. So here we can have a sulfuric acid to react with the alkaline sodium hydroxide. That would give you sodium sulfate, which is soluble, and then water. Okay, so in this reaction, because it produced water, so it will undergo this double displacement reaction. And for B, okay, I can also give you an example. So if we have hydrochloric acid, and we also put sodium carbonate, then we would have sodium chloride formed, which is soluble, and then water, and also we would have carbon dioxide. Okay, so again for this one, because it got water formed and also a gas that we're going to escape from the solution, from the system, right? So this double displacement reaction will take place. So for this one, you can think of like this. Okay, so after the double displacement, we should have a sodium chloride and also carbonic acid. But remember, carbonic acid would easily turn back to water and carbon dioxide, so you write it separately. And for C, okay, produce precipitate, a solid. So that's also called precipitation reaction. Okay, so here I can give you an example, which is, for example, we can have silver nitrate to react with sodium chloride. Okay, and then it will form silver chloride, which is insoluble, and then we will have sodium nitrate, which is a solution. So for this one, because silver chloride is insoluble, so the reaction can take place, and we will call this special type of reaction precipitation reaction. Okay, so let's use this criteria to examine the two reactions we have here. So for reaction 6, okay, does it contain mobile ion? So first one, magnesium nitrate, since it's soluble, and we can make it an aqueous solution. So yes, it contains mobile ion. But take a look here. Zinc carbonate is insoluble, and we cannot dissolve it in water to form solution, and it's in solid state, so no mobile ion. So actually for this one, it would not have any reaction between these two substances. No reaction. How about the second one we have here? Second one, we have magnesium sulfate, okay, which is a soluble salt, so we can make it into a solution, so it will contain mobile ion. The second one, we have potassium carbonate. Again, it's a soluble salt, so we can dissolve it in water to form the aqueous solution. So if I fulfill the first requirement, yes, both of the reactants contains mobile ion, so they can exchange. And the second factor, okay, the product, does it contain water or gas or precipitate? Okay, take a look here. The product formed is our magnesium carbonate, which is a precipitate, is in solid state, and again, and also potassium sulfate, which is a soluble salt, so in aqueous state, okay, dissolving water. So if I fill C, okay, here, it produces a precipitate, a solid, okay, so if I fill 2C, so this reaction would take place. Okay, so we can put a tick for that, and let's consider whether the reactants suggested here are quite easy to make. Okay, so these two salts can be found and prepared in aqueous state quite easily. And then let's consider, can we easily separate magnesium carbonate from the two reactants? So magnesium carbonate, our target salt, is insoluble. The two reactants that we used here are in aqueous solution. So how can we separate a solid from the solution? Okay, so the answer is by filtration, using a funnel and a filter paper. So the solution contains the unreacted reactants, and also the side product will go through the funnel. So on the filter paper, it will left with the product that we want, which is magnesium carbonate. So we can put a tick for that. It's a perfect method for here. So if we go back to the worksheet, we can fill in the last two row. Okay, for this one, because no reaction, so we put a cross. And for the last one, yes, they're going to have a reaction, and we can easily separate the product from the side product and the unreacted reactants. So that's a perfect method. Okay, so that's one of the example. You can take a look. What is the best choice here? Okay, and now I'm going to go back to our notes and go through one more example with you. And I hope by going through these two examples, you can summarize the rules for making insoluble salt. Now let's go back to our notes, page 11. So on your notes, here it gives you the example is to prepare lead-2 sulfate. Okay, lead-2 sulfate, if you remember, for sulfate ion, we have two special insoluble salt, which is start with A and P. Okay, so it's lead-2 and silver sulfate. So how can we make lead-2 sulfate? It has suggested three methods. The first one of the students suggested that we can use lead-2 oxide with calcium sulfate. Okay, so for here we have both of them in solid state, insoluble. Okay, so again, by consider the requirements for double displacement reaction, okay, we can quickly find out that these two cannot have any reactions under normal condition. Okay, so when we put these two together, no reaction. How about the second choice, lead 2 oxide plus sulfuric acid? Okay, so lead 2 oxide is base, sulfuric acid is an acid, so base with acid, then neutralization reaction. Okay, so first we can circle that this reaction can take place. Okay, and it's a common neutralization reaction. Then we need to consider the second factor. Can we easily separate the product, the target salt, from the side product and also the unreacted reactants? So as you can see, since lead 2 sulfate is insoluble, it's going to coat on the surface of the lead 2 oxide, which is a reactant, immediately after the reaction. And it will stop further reaction, and we cannot separate the surface layer of lead 2 oxide easily. So again, this method is not practical. How about the third one? Third one, we have lead 2 nitrate, which is a salt, with sulfuric acid. Okay, this one. So both of them, nitrate salt and the acid, they are in aqueous state. So this one, if we examine the condition for the double displacement reaction, okay, first, both of them contains mobile ion. Then we can work out what are the product going to be formed. So the product, if they exchange the ions, then we're going to have nitric acid formed, and also maybe I write it down. You're going to form nitric acid and lead 2 sulfate. Okay, so these two are the product. Then let's check. Does it contain water? No. Does it contain a gas? No. And then does it condense a precipitate, a solid? Yes, here. Okay. The lead 2 sulfate formed is insoluble, so it would form something that's solid, a precipitate. Hence, this double displacement reaction can take place. Okay, so just circle it can take place, and after the reaction, it will form the target salt we want, which is lead 2 sulfate, and then it will form the side product, which is nitric acid. Okay, and the unreacted reactant, which is sulfuric acid and lead 2 sulfate. Okay, so as you can see, all except the target salt, lead 2 sulfate, everything else is soluble, okay, in aqueous state. So we can obtain the solid salt directly by filtration. Okay, so using the funnel and filter paper. So after going through these two, I believe you can see the trend. Okay, so in order to prepare the insoluble salt, e.g. the lead 2 sulfate or the magnesium carbonate, so we should use the reactant that are in aqueous state, so they should be both solution. Okay, so that the insoluble salt formed can be separated by filtration. And what is the solution we're going to choose? Okay, that's the next one that's the next point we're going to discuss. Okay, so in order to form the insoluble salt, so we would use a double displacement reaction. So that we need to separate the target salt into two parts, which is the target cation and the target anion. Okay, then we need to think about two solutions that contains the target cation and the target anion. Okay, so remember we need two solutions, and then after we put them together, they're going to form the insoluble salt, which is a precipitate for us in the target salt. Okay, so we call this kind of reaction double displacement reaction, and also it can be called as precipitation reaction. Okay, since it got a precipitate formed and insoluble solid formed here. Okay, let's try to fill in this table. So the first example, lead-2 sulfate, so the target cation should be lead-2 ion, the target anion sulfate ion. For lead-2 chloride, target cation lead-2 ion, the target anion chloride ion. Silver chloride, the target cation should be silver ion, and the target anion should be chloride ion. So now we need to suggest some of the solutions that contains those ions. So for the first part, the solution contains the target cation. We need to have a salt solution that contains those metal cations. Okay, so what kind of anion or what kind of solution that's when it combined with a metal cation, it's always soluble. So the best choice here is a nitrate salt. Okay, so because all the nitrate compounds are soluble, okay, so to be safe, you just need to put lead-2 nitrate for the first two. Okay, and the last one, you just need silver nitrate. Okay, they are all soluble solution that contains the target cation. Okay, remember in this part, we are going to discuss one possible way to make it. It's not the only way. Okay, since there are other options of there are other options of solution that contains the target cation. Okay, so if you are really familiar with the solubility table, then you can choose other compound. Okay, but to save your time or to begin with, I would suggest you just to use the target cation with the nitrate and make it the solution that you suggest in making the soluble salt. Yes, making the insoluble salt. And then the next part, we're going to consider another solution that contains the target anion. Okay, so for the solution that contains sulfate ion, maybe a lot of you quickly think of sulfuric acid. Yes, that's a good choice. And for chloride ion, yes, hydrochloric acid, that's a good choice. Okay, so we can write that down. Sorry, this one should be hydrochloric acid. Okay, and because we just need a soluble salt, so it can be group 1 salt. Okay, because group 1 or ammonium salt, they are all soluble. Okay, so you can also write other possible solution, maybe potassium sulfate. Okay, that's also possible. And for the rest one, maybe sodium chloride. So you just need to consider or potassium chloride. Okay, again, that's just some of the possible solution. I'm not going to list out all the possible solutions. When you suggest a solution, try to provide some common one, so it's easy for us to obtain the materials to prepare the salt. Okay, and after we decide those possible solutions, possible reactions, we can write the equations for the above reactions. Okay, for the first one, if we choose to use lead-2 nitrate, for example, here I choose the sulfuric acid, and then the product would be lead-2 sulfate and also nitric acid. Okay, and then we fill in, we balance this equation first. Sorry. Okay, and then we write the state symbol. And for the second reaction, maybe this time I choose another salt. So again, I choose lead 2 nitrate. Okay, this time I choose sodium chloride. So the product would be lead 2 chloride with sodium nitrate. Okay, remember to balance the equation and then write the state symbol. And for the last one, if I choose silver nitrate with hydrochloric acid, and then I will get silver chloride with nitric acid. Again, try to write the state symbol accordingly. Okay, so that's how we prepare insoluble salt. Okay, so after going through this theory part, let's discuss what are the procedures involved in preparing the insoluble salt. Okay, so for this one, it's pretty simple. First, we just need to mix the two solution, and then of course we need to mix it or stir it, and then make sure the precipitate is well formed, and then we filter the precipitate and then wash the precipitate with some DI water, so we are not going to contaminate our target salt. And then we dry the precipitate by using filter paper or an oven or an desiccator. Because now we cannot do lab, so please refer to this video for the details. And when our class, when the school resumed, I will let you to do this experiment on your own. In the last part, let's go through the checkpoint questions. Again, please pause the video here, attempt all the questions, and then listen for explanation. Okay, let's go through the question together. Question 1. Which of the following solutions will form a precipitate with silver nitrate solution? Okay, silver nitrate. So first one we have potassium bromide. Okay, so when it react with silver nitrate, the possible product would be silver bromide plus potassium nitrate. Okay, so again, all the nitrate salt or group 1 salt is soluble, so potassium nitrate would be soluble. How about silver bromide? Okay, so for bromine, it's an halogen, and for the bromide salt, only 2 exceptions you need to remember, which is silver bromide and lead 2 bromide. They are insoluble. Okay, so here we are going to form silver bromide, which is insoluble. Okay, so we can put a tick for option 1. How about the second one? If we mix silver nitrate with sodium carbonate, the possible products would be silver carbonate and also sodium nitrate. Again, group 1 and nitrate salt, they are all soluble, so we just need to check whether silver carbonate is insoluble. And for carbonate, you just need to remember only group 1 carbonate and ammonium carbonate, they are soluble. The rest of the carbonate salt, they are insoluble. Okay, so silver carbonate is insoluble. So again, the second one would form a precipitate with silver nitrate. The last one, we have hydrochloric acid with silver nitrate. So after they exchange the ion, it will form silver chloride with nitric acid. So silver chloride again is insoluble, so we can put a tick for that one. So the correct answer should be D. Second question. Which of the following pairs of solution will form a white precipitate when they are mixed? Take a look. The first one, let's check. First, they are all in aqueous solution, so they contain mobile ion. Second, would they form any precipitate? So if they would have a reaction, then the product would be potassium nitrate, and also lead 2 sulfate. Okay, so again, potassium group 1 ion, group 1 salt, nitrate salt, they are all soluble, but lead 2 sulfate is insoluble. Okay, so the first one would form a precipitate. How about the second one? For the second one, okay, what's going to happen when we react ammonia solution with iron 2 nitrate? So what's going to happen in ammonia solution is that the ammonia would react with water and undergo this reaction to give out ammonium ion and hydroxide ion. And then this hydroxide ion would react with iron 2 ion and then give the precipitate, which is iron 2 hydroxide. Although it would form a precipitate, which is iron 2 hydroxide, but pay attention to the question. It asks you which one will give you a white precipitate. Remember, iron 2 hydroxide is not white in color, so we should not put a tick for the second one, okay? Since it's not white precipitate, so we should not choose the second one. How about the third one? The third one, we have ammonium carbonate with calcium chloride. Let's try to write out the possible products. So it will be calcium carbonate with ammonium chloride. Remember, all the ammonium salt are soluble, so this one is soluble. How about calcium carbonate? So for carbonate, remember just group 1 and ammonium carbonate, they are soluble. The rest of them insoluble. And it's white in color, so this one would give you a white precipitate. So the correct answer should be 1 and 3 only, so we should choose B.